Good morning, everyone. I am Jorge Simón, a PhD student at Universidad Carlos III de Madrid in the Aerospace Engineering Department, and today I'm going to talk a little bit about my thesis entitled Dynamics and Control of Spin Electrodynamic Tethers Applied to Space Sustainability under the supervision of Professor Sánchez Arriaga and Dr. Batanja Kadim. So first, a little bit of introduction of the technology that we are working on in our project. So electrodynamic tethers are long conductors that orbit and that have been extensively studied for diverse aerospace applications, such as propellantless propulsion for the orbiting, reboosting, station keeping, among many others. As the tether system moves at a given velocity through a conducting plasma and a magnetic field, an electric current can be induced along its length, and due to interaction between this electric current along the tether length and the geomagnetic field, a Lorentz force appears. So if these systems are placed along the local vertical that is pointing toward the Earth, a dynamic instability appears due to the continuous pump of energy from the electrodynamic forces that can cause the system to oscillate around the local vertical, or if it is not controlled, if the system is not controlled, to spin. So an alternative configuration to avoid this type of instabilities is to place directly the system into the spin condition, which in addition provides more flexibility to the system to be oriented relative to the geomagnetic field, which is particularly important for high inclined orbits because the vertically aligned tethers are much less effective. Okay, so here I will explain a little bit of the motivation of this work. So first of all, it was found that the orientation of the spin plane is a crucial aspect to reach high performances for spin electrodynamic tethers for orbital maneuvering, for instance. However, this spin plane is really affected by external disturbances such as the gravity gradient or Lorentz force. The dynamics of the spinning electrodynamic tether system, it's really different from the dynamics of the typical satellites due to the elasticity properties, the inability to compression of the tether, and a negligible axial moment of inertia. So, due to this factor and that the number of spinning tether missions is very low, the knowledge about this system remains scarce. So, apart from that, studies, the few studies that exist in the literature mainly focused on transverse and axial vibrations, and only a few works analyze the attitude dynamics, but always restricted to planar motion or circular orbit, so with simplifying assumptions. So the motivation is to develop a model to study in detail the attitude dynamics of these kind of systems for circular and elliptical orbits, for high spinning tethers, with our in-depth analysis of the stability of the different configurations of these systems. And for the model, we consider a straight rigid and linear tether with a given mass and a given length that joins two endpoint masses S and B. We also consider that the moment of inertia along the tether's direction is zero, and that the motion of the center of mass is prescribed and follows an unperturbed Keplerian orbit, assuming also that the right ascension of the ascending node and the argument of perigee are both zero. I introduced two frames, the typical inertial frame, Earth-centered inertial frame, and the typical orbital frame with origin at the center of mass of the tether system, and a body frame whose attitude relative to inertial frame is given by these three angles, three Euler angles, theta, beta, and bar phi, that are obtained through a sequence of rotations 3, 1, 3. So the vector IB is along the tether's direction, the vector KB is perpendicular to the plane in which the tether is spinning, which we call a spin plane, and the vector JB completes the triad. So just let you know that from these two equations, the angular momentum equation and the system's angular velocity relative to the inertial frame equation, where this omega perpendicular is what we called spin rate, and after some cumbersome algebra, one can find this set of equations that govern the attitude dynamics of the spinning tether system, where you can see that the three angles and the normalized spin rate, the variation of these parameters only depend on the dimensionless external torque about the center of mass and the current state of the spinning tether system. Then, assuming the gravity gradient as the only perturbation and substituting its expression into the previous set of equations, we obtain the equations that you can see in the box. And here you can see that the normalized spin rate appears in the denominator for theta and beta and appears as a separate factor for the variation of bar phi. So, assuming that the tether spin fast, that is that the spin angular velocity is much larger than the orbital angular velocity, we find that the timescale of variation of theta and beta is much larger than the variation of the fast variable bar phi. So we then can average the dynamics equations, the attitude dynamics equations over one tether revolution to find the slow time evolution of the tether system. And after averaging, we find that the evolution for theta and beta, using as an independent variable the true anomaly, are completely decoupled from the fast variable bar phi. And in addition, that the normalized spin rate is constant in average, so it becomes a parameter of the system together with the eccentricity and the inclination of the orbit. So we have reduced the system to a set of equations, of two ordinary differential equations of first order to describe the dynamics of the spin plane. And here I'm going to show you some animations to have a better picture of the real motion of the spin plane. So here you can see the Earth-centered inertial frame. We remove the Earth. Then an orbital frame with an inclination of 50 degrees. We remove everything except of the perpendicular vector to the orbital plane. Then a body frame in which the spin plane is within the orbital plane, because it corresponds to an equilibrium position of the system. So the spin plane dynamics equations that we obtained before have two equilibrium positions, two equilibrium configurations. One is for the spin plane within the orbital plane and with the vector kb along the direction of the vector ko, and the other one is the same position but with the vector kb in the opposite direction of the vector ko, which is the direction of the orbital angular momentum. So we introduce the body frame, the spin plane and the tether, and we remove them, okay? And here the animations that we are going to see corresponds for the spin plane evolution for a highly elliptical orbit, that is an eccentricity of 0.75, and for three different initial conditions. The first one corresponds for the spin plane slightly perturbed from the equilibrium point. The equilibrium point is for theta equal to 0 and beta equal to 50 degrees. So here we use as an initial condition 51 degrees. And the spin rate equal to 8. And as you can see, the equilibrium is stable because the spin plane remains oscillating with a very small amplitude around the equilibrium. For the second scenario, we use the same initial conditions, but for an inverse rotation, that is, the vector kb is in the opposite direction to the orbital angular momentum direction. And as you can see, the spin plane diverges from the equilibrium position and moves away from it, that is, the equilibrium position is unstable. And for the last one, we chose a periodic orbit that appears from the instability of the equilibrium position, and you can see here that the motion of the spin plane is oscillatory and periodic, completing one full revolution of this periodic motion after two orbits of the system around the Earth. And here you can see the three motions at once to better differentiate the motions. Okay, so here you can see the research objectives. We first started by the analysis of the optimal spin plane configurations. Then we started with the dynamics of fast spinning inner tethers. That is what I showed you in this presentation. Then we want to study the dynamics of spin electrodynamic tethers, that is including the electrodynamic forces, because up to now we just assume that the gravity gradient is the only perturbation. Then we will analyze some control laws, and we develop algorithms to apply active control to the spin electrodynamic tether system. And after that we will carry out some high fidelity simulations for some study cases of interest. And well, here you can see the achievements of the thesis up to this date. Thank you very much.